So, who am I? I'm a staff engineer at Ooyala. We'll tell you more about Ooyala in just a second. For the last couple years, we've been building real-time web-scale systems on top of Cassandra, Kafka, Storm, other big distributed systems like that, Hadoop. We're very excited to share with you today some open source projects that we believe is game-changing. And my Twitter handle is there in case you're interested. We're going to talk a little bit about what we do at Ooyala and how we use Cassandra. What problem are we trying to solve today? And a little bit about Spark and Shark and how you use it. So without any further ado, let's get right into it. So Ooyala, what our mission is to power personalized video experiences across all screens. That means that whenever you're watching, for example, you go to ESPN.com, you're using our technology. You go to some of our other websites, you're using our technology. We were founded 5 years ago by Google engineers. Since the very beginning, we've been focused on big data analytics. We get a huge amount of data that flows in from a lot of consumers that watch online video. And we are trusted by a lot of the top names in media, including ESPN, Pac-12. You can all see it there. We're a fairly large Cassandra user. We have 11 clusters ranging in size from 3 to 36 nodes, about 28 terabytes of data managed. We write over 2 billion events into a Cassandra data store. It's probably close to 3 every day. I think that averages out to about 15 to 20,000 events per second. This powers all of our analytics infrastructure. Cassandra powers all of our analytics infrastructure, from recommendations, raw event storage, trend detection, aggregated analytics. And we have a much, much bigger cluster coming soon. So we're pretty committed to Cassandra. What problem are we trying to solve? Where we want to go is from mountains of useless data to nuggets of truth. And we want to do this quickly, painlessly, and at scale. I guess this is sort of like everyone's big data problem. Today, what we have a lot of pre-computed aggregates. We have video metrics that are aggregated along several high cardinality dimensions. For example, we have URL, and we have what city someone's watching the video, what is your user agent, your browser, device type, that sort of stuff. And these lookups are very fast because they're all pre-computed along all these different dimensions. But the problem is that it's a little bit inflexible. It would take us a long time to change the pattern of writing this data. And the other problem is that most of these aggregates are actually not read, because it turns out that most customers are not really interested in video metrics sorted by every single city. There are a few key things that users look for. And now what happens if we need more dynamic queries? For example, we want top contents for mobile users in France. So that right there is 2 different dimensions. So now you start having cross products, right? If this was not France, but some city, so how many different types of browsers are there? And how many types of cities are there? So you start having this giant cross product, right? And let's say that we want to do data mining, trends, machine learning. If you look at, there's really a continuum. On one end, you have 100% of your data being pre-computed, which is where we are today. It's pretty fast, but it's pretty inflexible. It's good for kind of like maybe the top 80%. of queries. On the other end of the spectrum, you have 100% dynamic. Here you can query for exactly what you want, but it's very flexible, but it's usually pretty slow. And what I think we really want is we want something in the middle, something that is partly dynamic, where you pre-aggregate your most common queries, but you have a system that's flexible and fast enough to do your interesting queries, and you can easily generate the materialized views that you need. So let's have a quick look at industry trends. We're starting to see some fast execution frameworks. Anyone heard of Cloudera and Impala? Pretty interesting project. You have in-memory databases that are coming out. There's VoltDB, Druid. You have streaming frameworks such as Storm that are coming out. Even in the traditional Hadoop data space, you're seeing more and more productive frameworks like cascading and Pig. So we want to take advantage of all these trends. So we started looking at Spark and Shark. So let's talk about why Spark and why Shark. What is it? So Spark is an in-memory distributed computing framework that can also write to disk. It was created by UC Berkeley 3 years ago. And initially, it targets problems that Hadoop MR is bad at. For example, iterative algorithms, where you need to recompute the same set of data multiple times or like iteratively, interactive data mining. So because of those goals, it is more general purpose. It has it's a pretty active user community, contributions from a whole bunch of different companies. Let's have a look at, let's compare the different paradigms. Let's look at Hadoop. So you have HDFS. You read data out. You map it. It gets written to temporary files on disk, shuffled to the reduce phase. Then you write data back to your HDFS. Now, usually, like a single stage is not enough for your job. So you usually need 2 or 3. So you end up writing data back to your HDFS, reading it back out, and you do this over and over again, right? So let's look at Spark. What happens in Spark is that, let's say you have different data sources. You read it out. That still happens. That's still I/O. But after that, things happen in memory. I'm doing a map. Then I can have higher-level constructs like join. I can join the 2 different data sources. This happens in memory. And then the really neat thing is that I have this intermediary so I can cache it. After I cache it, I can do transformations. The red lines indicate that the data flow happens in memory. And what we find is that throughput, that memory is really king. We did a quick study reading data from Cassandra when the cache is code, about that fast. When the cache is warmed up, we get a speed up of about 7x to 10x. Having a warm cache does do wonders for you. But it's really nothing compared to in-memory processing by Spark. And the other reason why we know that we're headed in the right direction is because developers just love it. Someone who works with us was able to write the first job in 30 minutes without knowing anything. It has a very high-level distributed collections API that makes it very easy to do data transformations. You'll see why I wrote this in a minute. You get the full power of a regular programming language. You have an interactive shell that makes it very easy to do ad hoc stuff and figure out what you need out of your data. And testing is extremely easy. Anybody tried to do real testing with Hadoop jobs? It's not very easy. So here's an example Hadoop word count. This is the typical word count example in Java. I had to fit this to 4-point font just to fit it on one slide, Here's the equivalent in Spark. That's it. It's night and day productivity. And for a lot of companies, developer velocity is really the only edge you have. So here's the Spark ecosystem. You have Spark, which is the distributed framework. Underneath it is an exciting project called Tachyon. What Tachyon is, it's like an in-memory acceleration for HDFS. You can actually use it without Spark, but it gives you memory speed access to your HDFS files. And then on top of that, they've managed to build pretty interesting projects, which kind of goes to show the flexibility of Spark. One is something called Bago. Sorry for the pixelated image. Anybody heard of Google Prego? Prego is Google's gigantic distributed graphing engine. So they've built a system like that on top of Spark. There is Shark, which I will talk about in demo in a minute. This is Hive QL on Spark. And finally, there's Spark Streaming. This is doing streaming computations on the fire hose. Let's say your Twitter fire hose that comes in, and you do discretized, which means that you're processing data in small chunks. So more on Shark. Shark is built around Hive. So how many people use Hive in here? So fair number. It's 100% Hive QL compatible, but it's about 10 to 100x faster. You can get answers in seconds. There's no need to compile an MR job. You can reuse all of your existing UDFs, storage handlers, SerDes. And you can use, if you use DataStax Enterprise, you can use Cassandra FS as your Hive metastore, or you can just use HDFS. There's also a really neat feature that you can write Scala Java integration. Hive SQL is good for a lot of things, but for more complex creation materialized views, you need to create UDFs, and you need to package it, ship it. I personally would prefer to use a real programming language to create some of these jobs. So having this integration is actually really, really powerful. But anyway, enough about Spark and Shark. What we really want to get to is how are we using it. So we start off with raw events. What we call raw events are, let's say you're watching a video on your mobile phone or desktop. Then we have a player in Flash and JS that's sending events to our servers constantly. So these are what we call the raw events. They're the raw video pings. From there, we have a real-time ingestion engine that writes these events into Cassandra in a matter of seconds. Then what we want to do is, from Cassandra, we want to use Spark to create different materialized views. And on the one hand, you can use Spark for predefined queries. And maybe for more ad hoc stuff, you can use something like Shark, which gives you Hive QL, SQL. This is our stack. You have Cassandra Notes. On top of Cassandra Notes, we've written a custom input format that reads from our schema. And on top of the input format, there's something called a SerDes. If you don't know what a SerDes is, it's basically Hive's way of mapping Hadoop data into Hive, into a table. And we'll talk about that in a sec. And on top of that, we just have Spark, which is controlled by master and a job server. Just a little bit about our schema. We have a time series schema. This might look familiar to a lot of you guys, but let's say you have a user. User has events coming in, so you have every column is like a different point in time. So pretty standard. We have, however, split out attributes into a separate column family. The reason why we do that is because let's say you're a user. There's a lot of data. Your user agent, your IP address, that pretty remains static during the whole day or whatever it is. And if you were to write that again and again into every event, you'd be wasting a lot of storage. So we separated it out. And this also gives us an extremely nice way of doing indexing and filtering. For that reason, we can't just use the built-in Cassandra input format. We write our own. But it works in a similar way to, how many people have used CQL? So the way that we unpack the raw events is that we take an event, and you unpack some fields into a table, and you go in row order. So you go from T0 to T1. And then when you reach the end of the row, you wrap around, and you go to the next user. what we get out of this is that we get all the data for one user in consecutively, which for us gives us a lot of interesting data processing. Just really quickly, if you are interested in writing your own input format, it's important to know what API to target. There's a new input format Hadoop API and an old API. Hive only supports the old API. Cascading, maybe something else. You should be prepared to spend time tuning your split computation. You don't want to spend minutes reading very large index rows. If you want very low latency, you might need to do some tricks to estimate the size of your indexes, things like that. You might want to consider sorting row keys by token for data locality. Finally, Hive has an interesting feature called predicate pushdown, which is where if you have a where clause, Hive can actually send that information down into the input format so that the key thing in these jobs is that you want to reduce the size of data you're reading. So you don't want Hive to, or the Shark in this case, to be doing the filtering in memory. You want to minimize the number of rows you're reading from Cassandra. So that's pretty important too. So here's an example for OLAP processing. We start up with the events in Cassandra. We create OLAP aggregates, which are the materialized views. And we do a union. So let's say that we want a certain time range. These represent different time range. Maybe this is an hour ago, this is half an hour ago, this is now. We do a union of the data. Then we can do different queries out of that data. The performance numbers that we're able to achieve is, for example, for reading data out of Cassandra with the code cache, let's say it takes about 2 minutes. The cache is warm about 20 to 30 seconds. And then we generate the aggregates in memory. Reading the aggregates in memory is way less than a second. So you can imagine this opens up a huge number of possibilities. So I just want to go into our workflow a little bit. What we do is that we have a REST job server that sits in front of Spark. This is our Spark as a service layer that it also gives us a nice boundary between between teams, because teams can just use a simple REST API to submit their jobs. We start up an aggregation job that will pull data from Cassandra, writes into a data set. The data set is split across nodes, so each of these boxes represents one worker node. And then what happens is that you have a query coming in. This starts a query job that is a distributed job, reads from the data set, does a bunch of number crunching, and gives the results back. And then you can do this repeatedly. But what happens if there's a fault? Right, this is always the big question. So cache data sets only live in a Java heap. What happens if the process dies? Spark has something built in called Lineage, which is that when there's missing data, it remembers the steps that it takes to transform the data. So it can always go back to the source, which in our case is Cassandra. And it can do this recomputation for you. But this is fairly slow. If it takes 2 minutes or 30 seconds, that's not really an acceptable delay. However, it can also replicate cache data sets to two different nodes to survive the failure of any one node. Now, if you combine that with actually persisting materialized views, then you have a pretty good solution. You can have multiples of these processes running, and you can load whichever data set you want out of Cassandra or out of Tachyon. Yep. So just want to show you guys a really quick demo. I'm sorry, I really wanted to do this demo live, but it was really difficult to get equipment cooperating. So instead, I've made a little QuickTime video and some screenshots. So if you excuse me, this is actually just running on my laptop. I didn't really want any network problems. We're going to demonstrate how to create a table from Cassandra with our input format and querying data out really quickly. So creating a table from Cassandra basically you do a create external table, which creates it's basically a table view on Cassandra data. And the key points, we need to set the storage handler that we use, which is the custom input format that we told you about. And then you set in the table properties, you pointed at, OK, these are the Cassandra nodes that we want, the port, key space, start time, end time. It's actually very similar to the Cassandra input format, if anybody's used that. So now that doesn't actually read data out of Cassandra. That just defines the table. And actually, if I go back, the most important part is that there are fields here. So the event type provide ID, those are actually fields in our JSON. Well, it's actually not JSON anymore, but those are actually fields in the event map. So every time you create a table, you're saying, I want these fields, these fields, these fields. And then the magic is that I create a cache table. And this will actually pull data out of Cassandra. In this case, this is a little bit of a trivial example. I'm creating a table that's exactly like the data in Cassandra, except that it's cached in memory. In reality, you would probably be doing some processing on it. And this is the video. I'm going to try to count the rows for my cache table. And you can see this counts 1.4 million rows in just half a second. Don't try doing that in Hive. And let's say that I wanted to group my events by provider, which is a customer. And now this comes out very fast. And now I have counts by provider. But and you can see how fast and interactive this is, which is just amazing. But let's say that I want to do top K, because this is sort of like, I don't know who are the most interesting ones. So then I can just add an order by clause. I'm going to do order by count, descending, limit 20. And again, this takes just a second. Right, so these are my top providers. Thank you very much. You can reach me at my Twitter handle. Finally, we are hiring. I'm not sure we have any time for, we can probably take one or two questions.
Any
and
questions?
Then we'll be available here afterwards.
Questions, anybody?
I think there's a gentleman here.
Why did you choose Spark Shark over Cloudera Impala? Did you hear the question?
Yeah, so I think the question was, why did we choose Spark and Shark over Impala? That's a good question. I think Impala, one reason is that we have a big investment in Cassandra. We want to stick with our Cassandra investment with the data. The other reason is because we believe that Spark and Shark are a lot more general purpose, that we can actually write very easily Scala, Java, Python programs to crunch your data. We don't think that SQL gives you the same, like anywhere near close to the same productivity. Productivity. Maybe one more, and I'd be happy to take questions later.
Do you use Bagel for anything?
Sorry, I can't hear you.
Do you use Bagel for any of your applications?
Oh, did you say vagrants?
Bagel.
Sorry. Oh, Bagel. Oh, no, we haven't used that yet. That would be pretty interesting, but yeah. Right. Yeah, thanks. I'd be happy to answer questions here.